Taking growth and decay individually allows you to completely understand the concept. Growth is a mathematical change that increases without a limit, whereas decay is the rate of change that decreases and which must reach a limit, i.e. a horizontal asymptote. Culminating these ideas best show how growth and decay is a preferred way to describe the rate of change in relation to another variable. Both of these can be represented with an equation based upon its respective exponential function, hence conveying its particular growth-decay rate.
There are two forms of exponential growth and decay shown next to me. One is your general exponential function, and the other is a continuous exponential function. Both use an initial starting value at time 0 and a time period which has passed since the starting value. Our general function uses a decay rate in percentage, and our continuous exponential function uses an exponential represented by the letter E and a constant which is represented by the letter K. However, from both forms, we can acquire a final value which is the amount after the growth or decay.
However, this model assumes that these processes are constantly increasing or decreasing, not accommodating for outliers in the data. The use of radioactive materials in medicine wouldn't be made possible without this theory. Radiation, specifically the use of iodine-131 to treat thyroid cancer's half-life, ensures the survival of the individual, as well as the eradication of the cancer, although this medical treatment does cause other problems depending on the amount of iodine used. The other graph shows that radioactive traces decay faster, allowing them to be used more within medicine because they don't affect the body as much.
Additionally, another assumption that sometimes isn't taken into account is the limit in which the function reaches, whether that be for either growth or decay, and this effect on the human body. For example, these limits are based upon statistical rates. So within cases like cancer within the human body, it doesn't take into account the individual person and their reaction to radiation. This human error, based upon the nature of the individual bodies, may not align with prior regression of any exponential decay statistics.
By observing exponential growth and decay functions, we can gain insight into past or future occurrences. For example, if we look at the current growth of COVID-19 cases in the United States, we can understand the quick spread of this virus. This data on the graph shows that we can see a visual representation of this growth. According to the figure on my left, we can see that as of the 15th of February, which is our initial time, t is equal to 0, where there has been 0 recorded cases of COVID-19 within the US. Then we reach March 14th, the number of cases exponentially increased to just under 4,000. As you can see with this exponential function, there is a period of stability and then a rapid increase, as you can see from this exponential function, around the 10th of March. This hence allowed our government within Australia to learn from other countries and their exponential growth, allowing us to make proactive choices to flatten our potential curve.
Another example of exponential growth that has massive social and environmental impacts is the occurrence of climate change. The emission of CO2 being at the forefront of political and scientific debate conveys how much we need to be aware of the dramatic increases and how this will affect our ecological and fragile atmospheric world. Looking back at history with innovative occurrences of the Industrial Revolution, we can see that we are dealing with increased problems of emissions of gases today. In accordance with the graph, we can see that there's been a great increase of CO2 since the 1900s.
The models that assist in calculating and determining the functions of growth and decay are logarithmic functions, differential calculus, and integration. The models are approximation and are a common way of identifying predictions for growth and decay, annotating and graphing exponential functions using a constant of k for a continuous rate of growth can assist in recognizing the time passed through intervals of a sample size. Overconsumption and restraint in order to reduce resource depletion and environmental degradation can also be distinguished through growth and decay models.
In conclusion, exponential models of growth and decay are fundamental in estimating past and future occurrences. It allows us to determine the decay of substances like iodine-131 in the treatment of cancers. Alternatively, exponential growth functions indicate the growth of such instances as coronavirus and climate change in our current world. These models assume factors such as outliers, statistical assumptions, and human temperament with individual thresholds. Using regression in both decay and growth, it allows us to gain insight in the aforementioned occurrences. This has great implications for social, environmental, and ethical situations because it is able to give scientists, and particularly governments in our globalized world, foresight into future events.